All right. I will.
Every time I'll be Matthew. Matthew.
I will begin.
Daniel, not Matthew. Sorry, brother.
I will begin with a word of prayer, as it is time to start. I'm trying not to yell at physics this semester, so let's keep it that way. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to just bless our work today, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I wanted to show you guys some pictures before I forget. So let me turn off the lights here for show and tell for a minute. So this is something I have, it's posted on the website. It's like, you know, it's one of the PDFs I have there. We haven't looked at this one yet. It's probably worth a second. Let me just open it in a different way. No. Sorry. Where did it do? Oh yeah, too many folders. Thank you. The question is, which one was it I was looking for? No. That fake download thing, it drives me nuts. Where'd it go? I'm sorry, guys. I tried. Let's see here. Try again. Save link as. Well, electric fields from point charges are supposed to be in there. All right.
Your browser's thrown insecure download blocked up on the top.
Really?
Go back to your browser.
Huh. All right. Well.
Nice big night.
Oh, fine. We'll just look at it in the inferior browser setting. All right, I give up. I was trying to look at it on its lonesome, but it's not meant to be today. Oh, well. So, no, that's not what I want. All right, so here is a picture of the Coulomb field. There's something called stream plot in Mathematica that allows you to, you know, picture vector fields in terms of their so-called integral curves. It's not quite right, see, because there's some vectors starting here and there, you know, and to be totally honest, the only place where a field line should start is right smack dab there, right? Because this is the Coulomb field. The only places where a field line starts is at the origin. That's the only place. So this is a numerical, you know, approximation, but it does give you some visualization. Like I said, it's just a little bit misleading. Like that's not a genuine start of a field line. So, but it does give you some sense of the picture, and that's kind of cool. So here's another one. Here's the Coulomb field with a negative charge at 1, 1, I think. Yeah, 1, 1. As you can see, all the field lines are flowing into there, right? See that? Here's another one. Here's 2-point charges. I put a positive charge at 1, 1 and a positive charge at -1, 1. So they're both positive charges. So as you can see, the field lines are flowing out of both of them. And so if it's like this, that's what it looks like. If you're up close, you can see that, you know, there's a place in the middle, if they're equal, and these are equal, where you'd have electric field 0, right? But then the field lines kind of get bunched up and they spread out like that. This is a relatively close picture of it. If you zoom out by a scale factor of 10, here's what that same thing looks like. See that? If you zoom out by a factor of 10, you can't see any of that local bunching up because you just have 2 positive charges, right? So for all intents and purposes, it's just the Coulomb field with twice the charge if you're like zoomed out. But there's still all that funky, fancy stuff going on right here. You just can't see it because we're zoomed out, all right? And yeah, so here is another one, this time with a negative charge and a positive charge. This is the so-called dipole field. We looked at the mathematics of this in class, yeah? And so as you can see, the electric field is flowing into the negative charge and flowing out of the positive charge. And this is the dipole field. And what happens if you zoom out here? What if we zoom out by a factor of 10? Is it gonna disappear? Like, what's gonna happen? Same pattern, right? Just, you can't appreciate the geometry of the physical separation of the charges anymore because they're so close. It looks like this is what the dipole field looks like if the charge and the negative charge are really close together, all right? And you know, in terms of magnitude, the magnitude of this field drops off like the cube of the distance between the charges as compared to the Coulomb field, which drops off like the square, inverse square, as opposed to inverse cube there. So that's a dipole. And so how about this? What's this one? I think this is another. Now, okay, so what this is almost a dipole. Check out this. It looks like a dipole close in, right? So what we're looking at here is 1.01 charge at 1,1, all right? And just minus 1 charge here. So the difference in charge is only 1%, right? Very close. So this is, I mean, you could not tell that this wasn't the pure dipole field if you're at this scale, right? It looks exactly the same pretty much as the pure dipole field. But what happens when you zoom out by a factor of 10? What should happen here when we zoom out by a factor of 10? What should we see? What's that? I guess that's my question. Should the field lines be going in or out? If we zoom out by a factor of 10 here, I've got 1.01 charge at 1,1. I've got minus 1 charge at minus 1, minus 1.
It should be going all out.
All out, right? Because if we take a big Gaussian sphere that encircles both charges, right? The net charge is 1.01 minus 1. So the net charge is 0.01 charge, right? So if we're very far away, we can't tell the physical, you know, we lose track of the physical separation of the charges. It should just look like the Coulomb field if we zoom out. And let's see what happens. So I zoomed out at the 100 scale, and I got this. So it's still kind of dipole-y, but have patience. At the 1,000 scale, though, if I zoom out to 1,000, like a 3,000 by 3,000, you can see what we said happened. But it takes a little bit for us to overcome the appearance of the dipole field. And as you can see, it's still kind of wonky in here. I mean, it's picking up on that. But if I was to zoom out maybe to 10,000, it would look just pure Coulomb. Oh, there you go. So any semblance of the disparity in the plus and minus charge and the local behavior of the field between the places where they're distributed, namely 1,1 and minus 1, is completely lost at this scale of 30,000 by 30,000 grid. So, so anyway, yeah. We can anticipate all these things with Gauss's law, yeah? You think about the charge enclosed should be equal to divided by epsilon naught should be the electric flux. Yeah. And so if I'm far enough away, I can't tell the difference whether one's at the origin or the other is at the origin. There's essentially an approximate spherical symmetry for these kinds of distributions if we go far enough out. Now, there are other things. Here I put 2 positive charges and 2 negative charges at opposite corners of a square. This is the so-called quadrupole field. The quadrupole field. I won't try to draw this one by hand. But as you can see, it's something else. And if you factor out, what do you think is going to happen here if we zoom out by a factor of 10?
Still all out.
You think it's going to look the same? Do you think it's going to like collapse to a dipole field? What's your conjectures, guys? Yeah.
It'll look like a dipole.
Look like a dipole. All right, we have 1 vote for dipole. No, it's still the quadrupole field. It's just that think about basically what's happening is the square is getting scrunched to a point, and all of the loopage is just sort of being more bulbous. That probably wasn't on your bingo card for today. Dr. Cook says bulbous. There it is. This is the quadrupole field. It doesn't matter how far we zoom out, it will always look like this. In graduate electromagnetism, there's something called the multipole expansion. You can take any electric field and expand it as a sum over the possible pole expansions, like the Coulomb expansion, the dipole expansion, the quadrupole expansion, so forth. I think there might be I don't think there's a tripole expansion because you can't balance 3 charges, right? But if you got an even number of charges, you can balance them out. So there is something called the multipole expansion that you study in graduate electromagnetism. This here, I don't know what this is. What do we got? A mess. I have two charges at 1, 1. I've got a negative charge at 1, 0. I've got negative 3 charges at -1, 2. A negative charge at -1, 1. 2 positive charges at 0, -1. What's my net charge? 2 minus 1 is 1. 1 minus 3 is -2. -3 plus 2. If I've not messed it up, we have a net sum. The net charge is negative of -1 unit. So I think probably what I'm about to do is just zoom out and show you. It gives you the Coulomb field pointing inward. Since I had another one that was Coulomb field pointing outward, you know? Let's see if it happens. All right. Okay. Yeah. I didn't do it? Oh man, what a disappointment. Oh well. So at this point I decided to go 3D. There you go. There's the Coulomb field in 3D. Well, it's not really the Coulomb field. It's kind of like the Coulomb field, but there's the spherically radially unit vector field, I think. And here is what happens if you try to plot the dipole field 3-dimensionally with Mathematica. And these little arrows circled out. It may be better in the current version of Mathematica. I don't really care. Honestly, like, did I assign you plotting electric fields with Mathematica? I did not. Why is that? Because I don't care. I mean, but it can be done if you want, and you can make better pictures than this. I'm sure there. I mean, there is a good website. If you like, just Google electric field plotter. There's PHET. I think they're by University of Colorado Boulder, maybe. They have these like online physics labs where you can actually plot electric field lines. I'm not going to try that right now because it requires Java, and I don't think my computer's up to date on the Java. So what can I tell you? Anyway, I just wanted to look through here just to talk about what field lines look like, because it's a little bit better if you can look at the computer-generated one as opposed to like me just drawing it. Yeah. So that's all I got for this part. Do you guys have any questions? Before I put this away, you can ask questions about other stuff if you want. No? All right, well. So let us talk about Gauss's law some more, because you can never have enough Gauss's law. So as you know, we have the charge enclosed is equal to the divided by epsilon naught, which is, by the way, the permittivity of free space. This is equal to the surface integral of the electric field over the enclosing surface, right? And that we have a symbol for, we just call phi sub e, right? Now here, the charge enclosed, it's also equal to the integral, the triple integral, over, let's say, v. This surface, we could call this S. So S is equal to the boundary of the volume, the boundary of the volume. And so we could integrate dq dv over dv, but of course this has a name. That's the charge density, so the rho dv. All right, so here rho is charge density. All right. Hey, while I've got all these formulas out here, let's do a little bit more. Let's do a little calculus 3 here for a change. So what do we have? Let me write it down. We have the flux, right, of the electric field dot dA over the boundary of V. And I guess I'll put a double integral here just because it is kind of a double integral, right? So the double integral, the surface integral of the electric field over the area, surface is equal to the triple integral over the volume of rho dV. All right, and I think I'm missing. I got to put 1 over epsilon naught somewhere. Where should I put it? I guess I'm supposed to put it over here, right? So I'll put that out front since it's just a constant. Now, how many of you have had calculus 3 already? There's a couple in here, I think. So you guys tell me, how can I trade the left-hand side for a volume integral? This is equal to the triple integral over the volume of what? Fill in the blank for me. What is that?
Could you do dA and dO? Like as in, you're integrating area and then length.
No, not that kind of thing. This is a theorem of vector calculus. It's the very end of Calc 3 we learned this theorem.
Is it? It's not.
It's like way easier to calculate flux using this theorem than to do it directly usually. It's not Stokes' theorem, it's the divergence theorem, right? There we go. So, all right, that was, all right, so the divergence of the electric field. Yeah? So this is one of the 2 big theorems we learn at the end of Calculus 3. For those of you who are in Calc 3, I'm sorry, spoiler alert. Yeah? So about a week before Thanksgiving break, maybe you'll hit this, hopefully. Now, so this is a fundamental law of physics, right? So which volumes is this true for? The yes, right? Okay, great. So what does that mean then? If I have this triple integral equals to that triple integral, what does that say about the divergence of the electric field? What's it equal to? What's that? Just, yeah, P, which is rho, right? And that epsilon naught, we got to throw that in there. And there you go. This, my friends, is Gauss's law in differential form. It is the local expression of Gauss's law. We usually use the integral form of this law in here because, well, that's just how you use it. Yeah. This is one of the 4 Maxwell's equations. This is one of Maxwell's equations. So let me show you something a little bit disturbing. If we take the Coulomb field, right, which is what? Q over 4 pi epsilon naught, right? R hat over R squared. So like for a sphere of radius r, dA is equal to r squared sine phi d theta r hat, as it turns out. And so if I calculate the electric flux here, how's that go? I'm integrating, q over 4 pi epsilon naught, pull that out. Then I've got the integral of r hat over r squared. But when you do the integral over the sphere of radius r, the rule is that you have to plug in the formula for the sphere, right? But the formula for the sphere is little r equals to big R. So my Coulomb field on the sphere just becomes r hat over big R squared. So that's my formula for E. Then I'm supposed to take the dot product of that with the surface area element, which works out to r squared sine phi d phi d theta r hat. What happens to the r hats? Truth in advertising here. The phi goes from 0 to pi, theta goes from 0 to 2 pi, okay?
Can you factor out the r hat?
Better yet, what's r hat dot r hat? Not 0. Oh, no. It's a unit vector. Any vector dot itself is its length squared. This had better be 1. Otherwise, it's very bad labeling. If you have a unit vector whose length is not 1, that would be shame. That'd be shameful. I feel deep personal shame. So thankfully that didn't happen. R hat dot r hat is 1. The big R squareds, they'd be canceling. And so you got yourself a q over 4 pi epsilon naught. Let's do the integral. So we got integral from 0 to 2 pi of our d theta, and then we got integral from 0 to pi of sine phi d phi. All right, I'm using I'm using an odd-ed mixture of physics and math notation at the moment. I'm using the physics notation for polar radius. For spherical radius, and I'm using the math notation for angles. So that way everybody's not happy, right? Okay.
Go ahead.
So what's the integral of d theta? This is low-hanging fruit. Pick it. What?
2 pi.
2 pi. All right, we got that. Integral of sine phi from 0 to pi.
1?
Ooh.
No.
I give you half credit for that. So that integrates to minus cosine phi. Minus cosine phi evaluated from 0 to pi, you got yourself a 1 plus 1, which is 2. So the integral over that piece is 2. So you get a 2 times 2 pi, all this. 2 pi times 2, right? Otherwise known as equals 4 pi, right? So sometimes this is denoted as d omega in like engineering books and stuff, because that's technically the differential of the solid angle. The total solid angle over a sphere is 4 pi steradians, whatever that is. So anyway, what do we got? We've got q over 4 pi epsilon naught times 4 pi, which is q. Well, that's a relief, isn't it? Right? But here's the funny thing. However, if you look at the electric field is q over 4 pi epsilon naught, right? And 1 over, let's say, x squared plus y squared plus z squared to the 3/2 power times x, y, z, like that's straight up the formula for it, all right? And if you actually calculate the divergence of the electric field, which would be like partial E1 partial x plus partial E2 partial y plus partial E3 partial z. If you did this actually works out to 0. This works out to 0. So then we're left with a little bit of a conundrum here, see, because we have the integral of E dot dA, right, over the boundary of the ball of radius r, which is equal to the sphere of radius r, right, by the divergence theorem is equal to the triple integral of the divergence of the electric field over the volume, which I'm calling the ball of radius r. But I just told you that that straight up calculates to 0. What's the integral of 0? 0. How's that work? Because apparently 0 is not equal to q over epsilon naught, yeah? Because we just calculated directly that it's q over epsilon naught. How can it be q over epsilon naught 0? What's the rub? You're like, you're just using a part of Calc 3 I don't know yet, so it doesn't matter to me. But it should matter to you. Some of you are electrical engineers. This is like a central story. It's like, you know, I don't know. It's like if you're a lumberjack, you'd know a story about Paul Bunyan. You know, you just know, right? This is like that for electrical engineers. Yeah. What?
I'm sorry.
So the devil must be in the details here, right? What's the issue? The issue is the context, right? Divergence theorem holds for what? It holds for vector fields whose domain is well defined inside the volume on which you're applying it. What's the trouble with the domain of the Coulomb field?
There's no.
What happens at 0? It's infinite, right? So can I apply the divergence theorem? No, I cannot. Not to the whole sphere. I have to apply it to like an annular sphere, like a sphere with a hole cut out of the middle of it, like a gumball. You know, and if I do that, then I can remedy this. But I can't actually include the origin. And so the way this is addressed is to say that the charge density of a point charge is actually given by the following. Q times, well, I think it's actually 4 pi q, if I remember right. Oh man, I can't remember. No, it's Q. It's Q, I'll get it eventually here, guys. A little rusty. Q times the Dirac delta function of R. And this Dirac delta function is a rather interesting gadget. It is defined so that it's 0 everywhere. Zero for R not equal to 0. And it's infinity for R equals to 0. However, it's like this. If you take the triple integral of the Dirac delta function of R times a function of R over dv, that just gives you f of 0. So it takes integration and it turns it into evaluation. I might be off with my, I'm like, yeah, I think that's fine. There's some normalization factor I'm thinking about, but I don't think it matters to our discussion. So anyway, this is obviously not the required part of the course, but I want you to know about it a little bit because there's no earthly way this is going to be covered in your Calc 3. And if you're electrical engineering, it's something you should hear at some point. So now you've heard it. So my experience with good students in the past is like they have my Calculus 3, and then they'll find me like 3 years later, and they'll be like, thank you. I know what you're talking about now. So my apologies. This is for the future, your future self, not your current self possibly. So, all right, anyway, now that I got that out of my system, let us do another actual Gauss law example. So domain matters, by the way. Like domain for vector fields matters quite a bit. But it's easy enough to forget about that. The larger theme here is that any place where you have the electric field like blowing up, being infinite, or having a discontinuity, that's a place where there's a concentration of charge. And the thing I just erased actually says that. So the divergence of the electric field tells you how the electric field's spreading out. And what that equation literally says is that it's only spreading out where the charge density is non-zero. But for a point charge, the charge density is only non-zero at the origin, if the point charge is at the origin. All right. So example 1, let us suppose that we put a charge Q here at the origin, and then we're going to put a spherical shell. This is a conducting spherical shell. We'll say A less than R less than or equal to B, all right, with charge 2q on it. All right. And as I explained last time, or at least I claimed last time, I'm going to claim it again. For a conductor, the electric field inside the conductor has to be 0. All right? So the electric field has to be equals to 0 inside the conductor. Sorry, I have problems. But and the other thing I neglected to tell you is that the electric field, it has to be perpendicular to the surface of the conductor as well. You can start to understand why that should be, right? If the electric field was not perpendicular to the conductor, what would happen to charge that was on like the edge? Like the parallel part of the electric field would push the charge along the edge, right? But we're in the electrostatic situation, so the charge has to stop moving. We're talking about all of the charges come to an equilibrium, all right? So here's the deal. If the electric field has to be 0 inside the conductor, we can apply Gauss's law to a sphere which is like inside the conductor, right? The flux should be 0 through that sphere, right? So we do that. So imagine a Gaussian sphere like this, all right? And we're going to put it at radius r. So suppose r is, between A and B. Okay? So then that says the electric field is equal to 0. So that tells me that the flux there should be 0, right? But on the other hand, I have that the charge enclosed, right, divided by epsilon naught is equal to what? It's equal to the Q at the center plus the Q on the inside. Well, let's just say Q at A for lack of a, better label. Right, so there's some charge that has to be at the inside edge. See, because if there wasn't, I'm sorry, these stupid monitors and there you go. So actually I can do better. I'm sorry, I just said do better. Admonish me. Sorry about that. There we go.
Need you on the Liberty football team.
What is football?
Is that like philosophical or rule rundown?
Is that with the circular, like the spherical ball with the white and the black on it?
In some countries.
Okay. So, sorry. My wife was taking a graduate physics course as an undergraduate because that's who she is. And there was a great confusion because the professor was giving an example of like football breaking symmetry or something because he was thinking about American football. But all the international students were like, what? Because of course it's like a sphere. I don't know, it's funny. So anyway, long story short here, what does the QA have to be? See, this forces us to make the QA to be minus Q in order that the electric field inside the conductor be 0. So this kind of question, there's lots of questions. If I start out by telling you, you've got a spherical conducting shell, it has a charge Q at the center, right? Then I can ask a variety of questions. I can ask, like, what's the charge on the inside surface of the conducting shell? What's the charge on the outside surface of the conducting shell, right? Given that it has 2Q net charge, right? And then I can ask another question, which is, what's the electric field inside? What's the electric field outside? Yeah.
Just to clarify, the QA is the charge on the inside radius of the shell.
Yeah, QA is here. Yeah, like right here. The charge, yeah. So it would be spherically it would be like spherically distributed. So like you could talk about sigma A, the charge per unit area would be QA, which is apparently minus Q divided by 4 pi a squared. So there's the charge per unit area uniformly distributed on the inside surface of the conductor. Yep.
And would that make QB be equal to Q or that?
Oh, I don't know. Now let's suppose, well, let's see here. We're given that the net charge is equal to 2Q, right? But what else is it equal to by logic? So by logic and the rules of the game that I've told you we're playing, which is that there's no charge inside the conductor because it all gets pushed to the edges, all right? Because the charge is free to move, so it's free to, all the charge is free to push each other to the edges, right? It's like, imagine a bunch of hooligans in an ice rink and they're all like pushing each other. None of them stay in the middle, right? They all go to the edge. Frictionless hooligans, all right? So, that'd be a killer band name. My brother was in a band once, as Slow Children at Play. So, yeah, I said it was retarded. But will that get me demonetized? I wonder. I don't know. Maybe. It was my brother. It was my brother, though, so like I'm allowed to say things about my own brother, right? I mean, all right, let me stop digging this hole. Let's see here. So I don't really want to edit this video. QA plus QB. I did try to use that word in like a YouTube comment, no, Yahoo comment, Yahoo News comment somewhere. And then like, it's like something like, it wouldn't allow me to put it. And then it had the audacity to tell me that it wasn't censoring. Like in the response, it said it wasn't censoring comments, but something like that was against community standards. It's like, wait a minute, so you're not allowing me to use this specific word, but you're also telling me that this isn't censorship. I'm pretty sure that's the word I'm not allowed to say. Interesting. What's that? So out here there has to be QB. Yeah. QB has to be out there, and what does it have to be? So we figured out this is minus Q, so it must be that QB is equal to 2Q minus a minus Q, also known as 3Q, right? So QB has to be equal to 3Q by process of like elimination here. Algebra, yeah, algebra is a good answer. All right, now we figured out what the charge is on the inside, what the charge is on the outside. Now we can answer the follow-up question is what's the electric field everywhere? All right, so let me just tell you. So the electric field is equal to KQ over R squared radially outward for R less than A, right? Do you want me to prove it? I can prove it. Take a Gaussian sphere, right? Your favorite little Gaussian sphere right here, right? And if that sphere has radius r, then what's the charge enclosed? Charge enclosed is Q. So Q divided by epsilon naught is equal to E times 4 pi r squared. So the electric field is K Q over r squared because K is 1 over 4 pi epsilon naught. Essentially by fiat of what is a conductor, by properties of conductor, the electric field is equal to 0 for A less than R less than B, all right? And what happens if we put a Gaussian sphere outside of the conducting shell? Like out here. What's the deal? So like C, I have Q enclosed divided by epsilon naught, yeah, is equal to 4 pi r squared times E by the spherical symmetry. But what is Q enclosed of the green sphere? Nobody? I got what? Q plus minus Q plus 3Q. So I've got a net of 3Q. Because Q minus Q plus 3 is 3Q. So we get 3Q over epsilon naught equal to 4 pi r squared E. So lo and behold, E is equal to 3kq over r squared radially outward. For r greater than b. Now you might notice I have not talked about what the electric field is at r equals to a or at r equals to b. In fact, I can't talk about what the electric field is there because there's a local concentration of charge, right, for this idealized conductor. So like the electric field's not defined in the presence of localized charge. So I literally can't tell you what the electric field is at r equals to a or r equals to b. Yeah? Now I don't usually take points off a student in here if they accidentally throw r less than or equal to a or r greater than, I don't typically take points off if one of you guys were to do this. But, to be fussy, I shouldn't include equality there because it's not true. Not at least for this idealized conductor, which actually puts the charge literally on the surface of the thing. So, and the mathematical issue is essentially the same one that I raised with our discussion of like the divergence theorem and all that.
If you were to graph the three different E's, could you see it with the chain?
So, yeah, the graph of the three different E's is kind of interesting. So, like, essentially, I think I did a graph like this in the help session. So if you guys watched the help session from like last Friday, I did such a graph because we did such a problem in the help session. Something somewhat similar to this, but it was a little bit different. I mean, it was similar in spirit, but sometimes we throw in multiple shells to make it more fun. But the graph of the electric field versus the radius. So it starts out like Q over R, KQ over R squared, right? So it starts out like as a divergent. It goes to infinity there, right? So like that, until you get to what? You get to A, and you over here to B, right? So it's not defined there to be fussy. And then when you get to B, I guess technically you could imagine it kind of going like that, wherever that went to. It depends on what A and B are, But there would be some like logical continuous extension of that. And whatever it gets to, it starts again at thrice that. It starts there again, and then it like inverse square laws away to like that. So, and of course it's, to be fussy, it's 0 right in here, right? So that would be the graph of the electric field versus R there. Like I was saying, the jump in the electric field is an admission that there's a local concentration of charge there. We'll gain a deeper appreciation for this after test 1 when we start talking about potential energy per unit charge, or the potential. So I'll warn you, if you look at my old test 1, I have potential like voltage on there, and that's not on your test 1 because your test 1 is just about electric fields. So how to calculate the electric field, like by using Coulomb's law, taking the vector sum, or doing the calculus for it like we did, right? Or by Gauss's law. That's pretty much your test 1. So your test 1 is a little bit shorter than that test 1, all right? So yeah, and I think that's where I'll stop for today. So next time I'm probably going to do like an example where we have a half circle of charge, and we're going to find the electric field due to like a half circle of charge, some things like that maybe. Not really Gauss's law. I pretty much have I've said everything I have to say about Gauss's law in here at this point, I think. So thanks, guys.